The reason why this isn't done on an industrial scale is because it takes so much time to fill it up, do the distilling, empty it out, clean it out, and restart the process again. So we do more of a continuous style distillation. But what we call that is oh my gosh, you've got to be kidding me. We call that a continuous batch. And we'll talk about why we call that a continuous batch as well when we start talking about it. But the style that we don't really use in the industry very often is batch style. And then continuous batch is what we're going to be looking at with the tower. And then another style that we have that we use oftentimes in industry is fractional. Okay, and this is an example of fractional distillation. We'll pull this up on Simtronics here in a few minutes and so you see a lot more detail. But fractional distillation is different than what we talked about in the lab because fractional distillation, we're pulling off multiple materials. Okay, in the lab at Insert, we just had stuff coming off the top, stuff coming off the bottom. Here, we have all kinds of different points that we have material coming off. Okay, this would be an example of distillation unit and crude oil refining. Okay, so this is where we have crude oil coming in and we have all kinds of different lines coming out. The heaviest of components that never boils is our asphalt and things. The lightest components that boils the easiest can go out into become high octane gas, even propane and things like that. And then as it goes through these different components, as we go down the tower, are going to have a higher and higher boiling point. Okay, and so as these components come in the feed, we just simply separate them out by whatever point they boil at. And so regardless of where you go work, regardless of the industry, it's always going to have somewhat of this combination of equipment. Okay, at some point, we're going to have to preheat the material. We're going to have to heat the material as it goes into the tower. Okay, so to heat the material up, that's our feed. It goes in, and we heat it up once and bring it to its boiling point. Okay, and then it goes into the tower and separates from there. That's going to be done with some type of a feed pump. Okay, we're going to pump it in. We're going to have some type of either we call it a tower or a column. That's the main part. That's this part here in the middle. And then we have to add heat into the system, so we have to have a reboiler. And that reboiler is shown down here. We boiled it once before it got into the tower. We have to make sure it stays hot. We have to make sure it all gets separated. So we reboil it here at the bottom of the tower. That's where we add the main heat into the tower. Now, anytime we add heat in order to have good separation, we have to pull that heat back out at some point. Okay, and that's where this comes in right here. This is the condenser. Okay, the condenser is this heat exchanger right here. All the hot vapors that come off the top, eventually we have to condense it, and we have to cool it, and we condense it back down, right? And then after that gets condensed, we have an accumulator. We'll talk about that, so we don't really look at that in the lab, but that's another important piece. And that's where we have that condensed product from its vapor state into its liquid state so that it can be pumped back into the column. Okay, we pump that back into the column through a process called reflux. And we'll talk about why we use reflux and the importance of reflux here when we get into the next slide. And then the last part that we have of this is the bottoms pump. Okay, anything that doesn't boil off is our bottoms product, also known as residue. And so that has to get pumped into the next part of our process and so it's get pumped out of the column, out of the tower. And so we do that through the bottoms pump. This is the basics equipment that we use for a distillation system. This is a little bit more detailed, a little bit more expanded view of what we're looking at. Okay, we bring the feed in. Okay, right here we bring the feed in. In our example in the lab, this feed we called beer. Okay, so it had a combination of alcohol and it had a combination of everything else, all the residue and everything else. Okay. In the crude oil example, our feed would be simply crude oil. Okay. We'll have a mixture, an example that we'll use in Simtronics. It'll be some gasoline components, and we'll need to separate them out. That gets pumped into the tower. Okay. It gets pumped in halfway up the column, almost all the time. That's where we do it. Pump it in halfway. The reason being is we have a mixture here, and we want that to be able to separate. And so if we pumped it in right in the bottom of the column, and we didn't have enough time for it to actually raise its temperature and boil off, it would simply just go into the bottom of the column and simply get spit right out the bottoms pump. So what we have to have is we have to have some amount of time for that to actually be able to absorb as much heat as it needs to actually be able to boil and separate, okay? And so what we have is we have our feed material go in here. Okay. And so our feed material goes in through this exchanger, and at this point through this exchanger it's going to be around its boiling range. It's going to be pretty close to where the light material wants to boil off. Okay. The reason it's not boiling off is because it's still under pressure, because we have a pump. We talked about pumps in equipment class. They have a discharge pressure, so it's going to be under pressure, keeping it from boiling. And then after it goes through this pipe and it hits the tower, at this point right here, when it hits the tower, our light materials are going to be wanting to boil off, vaporize, and they're going to want to rise up, and they're going to want to go up the tower. We're going to want, the vapors are going to want to go up the tower. Okay, and then our liquids, our heavy liquids, they're not going to boil off. Okay, so you haven't hit their boiling point yet, so they're going to want to fall down. They want to go down the tower. Okay, now if this was a simple, easy distillation, we could leave it at that. But in industry, it's just not that easy, because like we talked about in the lab, what's going to happen, regardless of the materials, what's going to happen is some of this heavy stuff, it may not be its boiling point where it's going to want to all of it turn to vapor at once, but it is going to start to be carried up, and it's going to be start to carried up in its vapor form and its mist form. And it's going to be evaporating up, and it's going to want to kind of go up the tower as well. These light vapors are going to want to kind of attach onto the heavies, and they're going to want to pull it up the tower in a sense. Okay, and so to keep that from happening, what we have is we have all these trays. And so if any of this heavy stuff does start to go up the tower, it's going to hit this tray right here. Okay, and that tray is going to stop it and slow it down. Okay, tray looks like one of these. Okay, you can have a sieve tray, we can have a valve tray, or we can have a bubble cap tray. Okay, but at some point it's going to hit one of these trays and it's going to slow it down. So the vapor is going to be going up, but it's going to hit that tray and it's going to slow it down. Now, if that vapor hits that tray and it's light enough, okay, and it's this vapor state and it's this light material, then it's going to be able to push on through the tray. Okay, if you notice the pictures we had, they have holes in them or they have valves in them. They can allow the vapors to go up. And so if the vapors are light enough, they'll move up and they'll keep going up this tower. And it'll hit this tray, tray will slow it down. But as long as it's light enough, as long as that vapor is light enough, it'll keep going up each one of these trays, okay? And then again, it'll hit the tray, and eventually, if it's light enough, it makes it all the way out the top of this column, okay, all the way out, in its vapor form. Okay, so at this point, it's boiled off in its vapor form. The lab we were looking at, it happened to be alcohol, and it boils off in its vapor form. So it's in its vapor form. And then here, the lab we're going to look, or the Simtronics we're going to look at today, happens to be hexane, okay, one of the components of gasoline, and it's going to be off in its vapor form. Now, not really easy to store or handle things in their vapor form. It's hot, and so what we do is we condense it, okay, and we run it through a condenser right here. So the other side of this condenser is generally cooling water. We talked about cooling towers and everything like that before. But what it's going to do is it's going to condense it back into its liquid form. Okay? It's going to condense it back into its liquid form, and then that liquid is going to be stored in this accumulator. And this accumulator is just a working tank just to allow that vapor enough time to cool down and condense and to fall into its liquid form. And then what's going to happen is it's going to be pumped, okay, through this reflux pump. It's pumped through this reflux pump, and then where it goes from here is anywhere from 1/3 to 2/3 of the product that came out at the top is actually going to get pumped back into the tower, okay, into the distillation column. And the reason for that being is, the reason we have to pump it back into the tower is we need some source of cooling, some source to pull the heat out, because what's going to happen is all these heavies are going to want to go up and they're going to want to kind of trickle their way. It won't be quite as fast and smooth as the light components, but the heavy components are going to want to eventually work their way up here. And if there's nothing holding them back, they can eventually work their way out the top of the column. But what happens is it gets all the way, these heavy components work their way up eventually to this tray right here, and then it gets hit with a big roadblock. That roadblock is this cooled product, okay? This cooled distillate is on top of this tray. And so this tray is way too cool for this heavy component. So if any heavy components got up to this part of the tray, got up to this part of the tower, they're going to hit this tray right here, and they're going to stop. And then what's going to happen is they're going to condense in their liquid form. It's going to be way too cold for this to be in its vapor form. And so then what it does is it condenses and it falls down to this tray right here. Now, if you'll notice, each one of these trays has a little weir on them, okay? Each one of these trays has a little weir. If we go back to our picture of the trays, they each have a little weir. This is a weir right here, okay? This is showing a weir right along here. And a weir is like a dam, okay? And that weir is going to hold a level of liquid on each of these trays, okay? And so there's going to be a certain amount of liquid, usually about a half an inch or an inch or so of liquid, depending on how big the column is. And what that liquid does is that liquid holds on there, and that liquid is acting as a roadblock to any vapors that may be going up the column, okay? Also, what that does is that weir stops any of our light components from falling straight down the column, because remember we have this light components that's already been condensed. It already goes back into the column. We do that for product purity. But if we didn't have these trays and these weirs here, this could just fall straight down to the bottom of the column. We don't want that. What we want it to do is we want it to accumulate here, and we want it to stay towards the top of the column, okay? If we don't allow our light components to stay towards the top of the column, they could fall down and end up going into our bottoms product. Okay, so that's what we have the weir for. Now, eventually this weir will fill up and it'll spill over, and it spills over into these parts right here and shown right here and right here. And these are called the downcomers. Okay, downcomers take material from the tray and put it on directly onto the tray below. So whenever material spills over one of these weirs, it doesn't just fall straight down the column again, it's going to fall into this tray below. Right? And so some of this light products is going to be in its vapor state, and it's going to want to go up to the top of the column, but then some of it's going to be in its liquid state, and it's going to want to work its way towards the bottom of the column. Now, along with that material, that light material going to the bottom of the column, we have this heavy material going to the bottom of the column. And after it comes through the feed tray, it's in its liquid form, it does the same thing. It fills this weir up, fills this tray up, goes over the weir, goes down the downcomer, and fills this tray up. Eventually this tray fills up, goes over the weir, goes down the downcomer, and fills this up. And eventually it gets all the way down to the bottom. Okay, once we get down here, this is all bottoms product. What we have to do is we have to provide heat to the bottom of this tower to make sure that any of our light components that kind of trickle their way down, because they can over time trickle their way just ever so slightly, trickle their way through this mixture and get to this tray right here, this very bottom tray right here, then what's going to happen is we're going to blast this with a bunch of heat. Okay, so all of our liquids that go through here, it goes through and it goes through this reboiler, boiled it once in the exchanger coming in, and then we're going to boil it again through our reboiler, okay, and we're going to boil it up and we're going to pump it back into the column, and we're going to add a bunch of heat to this column, and then what that's going to do is that's going to make any of these light materials that happen to trickle their way down to the bottom, they're going to flash off, boil off, turn to their vapor state, and start going back up the column. Okay, so we had cooling at the top, we had heat at the bottom, and that allows us to separate. Okay, we call this continuous batch because we think of each one of these sections in between these trays like a batch style distillation. We're just continuously adding to them and taking away from them. But we have distillation happening in this tray at the bottom and each tray up. Okay. Some special terms that we see on this screen we need to make sure we're aware of. Everything above the feed tray is called our rectifying section. Okay, that's primarily where our distillate or our light materials hang out, and that's the rectifying section, also known as an enriching section. Everything below the feed tray we call our stripping section, primarily made of our heavy residue. That's in the bottom. That's our stripping section. So we strip out all the light materials. Okay. Bottoms product, also called residue. We have tops product, also called distillate. It doesn't not all the light material goes back to the reflux line. Somewhere about a third of it actually goes out. We call that distillate. Okay, and so we have one product that goes out here and another product that goes out at the bottom. Generally speaking, this is our higher dollar product that we have. Okay, generally speaking, this is our high dollar product, and this is our leftovers product. And we can have coming out of our system as well. It's not always the case, but generally speaking, that's how we normally have it. Okay, and so that's kind of the overview of what happens with distillation and inside that column, okay, and what that looks like. Here's a little bit more detailed picture that has a little bit more of the instrumentation, a little bit more of the controls and everything on it as well. This is really the same as the last picture that we looked at, except it shows how we have temperature controls, how we have flow controls, and how we have everything going up. This is the rectifying or enriching section at the top and the stripping section below the feed tray. It labels in the bubble caps and the weirs and everything like that for you as well. Also notice it gives a label of vapors going up the column, vapors going up the column, and then liquids falling down the column. And that happens all throughout each one of these sections. Okay. Now, since we're adding cooling at the top here, okay, and since we have cooling going in the top here, and we have heat being applied at the bottom here, okay, here we're cooling, here we're heating up. As we go up this column, these temperature transmitters are going to get higher and higher temperature as we get closer and closer to the heat source, okay, and a lower temperature as we get closer to the cooling source. So the higher up we go in the column, the lower the temperature is. So as we move up the column, the lower the temperature is. We'll show you why that is important whenever we get into Simtronics as well. Okay? But as we go up the column, we get lower in temperature. As we go down the column, we get higher in temperature. Let me take a minute there, check the chat. Does anybody have any questions before we go on and talk about the operating conditions of the distillation column? Do you have any questions about the general review of what happens inside the distillation column? All right. So next thing we want to look at is going to be the operating conditions and what it looks like. And so we have feed composition, and the rate is the primary thing and one of the first important things that we want to talk about. That feed coming in is going to have a certain composition. What composition means is it's going to have a certain percentage of the lights, and it's going to have a certain percentage of the heavies. And we have to know that going in, or we just have to have an idea of that going in, because then that's how we know how much flow we have going out the top versus how much flow we have going out the bottom. Okay, and so if we have 100 gallons a minute feeding our column, and we have 20% distillate coming into that, we know that we're going to have 20 gallons a minute of distillate coming out, and we're going to have 80 gallons a minute of bottoms product coming out. Okay. If we don't have that, what we're having a backup in the column, and we're going to have overlap at some point. Overlap means where we have incomplete separation, where we might have some bottoms product go out with the distillate or some distillate go out with the bottoms product. Now, unique about what's unique about this is that feed composition is almost always going to be changing. It's going to be changing a little bit, changing somewhat, because that's the whole nature of distillation. We're separating this raw material out and making good products out of it. And so as it goes through, that's going to change and that's going to fluctuate. And we need to be able to fluctuate the controls of our tower accordingly. We need to be able to adjust how much is going out for distillate, how much is going out for the bottoms. And like I mentioned during the lab, that's not a quick thing. Okay? If our feed adjusts by 10, 20 gallons a minute here, going in, we might not see that for 4 or 5 or 6 hours by the time it gets all the way up through the column and out the ends. So we have to keep an eye on that. Because if we make an adjustment for our feed, we have to remember that and know that and understand the adjustment that we made, because it's not going to instantaneously be shown coming out the column. That's going to be a delay of 4, 5, 6 or so hours coming out the back end. So that's important to remember. Temperature is something that we have to monitor. We have to monitor the temperature all throughout the column. Okay, we have to monitor the temperature in the pressure and the differential pressure all throughout the column, because that's going to tell us how the column is operating. Not only do we need to know the keys or the temperature coming in, the temperature going out, we have to know the temperature at different points throughout the column and then pressure at different points about the column, because that tells us what's inside the column. If this temperature starts going up, starts fluctuating, and starts getting higher, that tells us we have too much bottoms product at the top of our tower, okay? And we need to up the reflux going in. We need to cut that back. Because if we get too much bottoms product up here, then that means we have the chance of sending it out in the distillate, which is not good because it contaminates our distillate. And so we have to monitor that. And we monitor the pressure along with that as well, because the pressure is going to be relative, since we're boiling everything in here. Pressure is going to be relative to the boiling point, and pressure along with the temperature tells us what's in our column. Okay? And then material balance goes along with the feed composition. Whatever is going in has to be coming out. Okay? And then, like I said, it sounds really easy when we talk about it in the lecture, and it seems like an easy concept. If I have 100 gallons going in, I have to have 100 gallons going out. But the problem with that, and the hard thing for operators to realize, is if you make a change here at this front end part, it could be 6 hours before you see that change happen here. And so it's not like you're jacking this up by 10 gallons a minute and you're going to want to jack this up right away to 10 gallons a minute. You need to wait for that to actually get all the way through the system and then start adjusting the parameters of what's coming out of the column. And that's, once you get the hang of it as an operator, it's something that you can do and something fairly simple and straightforward. But for new operators, it's pretty tough to be able to understand that and be able to see that work and happen. And that's material balance. Whatever goes in has to come out. Because if it's not coming out, that means it's getting backed up somewhere, and that means we're contaminating one of those two outputs. And the other thing we have to balance is we have to balance energy or heat. Okay? We're putting heat in by the reboiler. To remember that we have to take that back out, the condenser at the top of the column. And so if we want to try to do faster or harder or run more, we can try to bump that heat up, bump that reboiler up as fast as we can go. But keep in mind that if we can't keep up with that on the outlet of the distillate, if we can't keep up with that on our reflux, then that means we're just going to get the overall temperature of the column hotter, which means we're going to send more of that bottoms product out our distillate. Okay, and so that means we're going to have overlap there. Okay. Also, if we're not putting in enough heat down here, if we're taking too much heat out, pulling too much heat out through that condenser, then that means the whole column can cool down. And if the whole column cools down, that means we end up with our distillate, our light molecules down here in the bottom and the residue. Okay, and so we don't like that either. So we want to make sure our light materials stay at the top and our bottoms stay at the bottom. Definitely safety concerns. Boiling materials, we got to have high temperatures in order to do that. Stuff's going to happen under flow rates and pressures, and these are going to be generally volatile chemicals that we're dealing with. They're going to be flammable, toxic. Anytime we're dealing with distillation, for the most part, we're going to be a classified environment. That's what we talked about in the lab. That's where I showed you all those extra electrical controls, all those electrical seals, and things that we can't have in there, because if we have any open sparks in there, then we could have the chance of a flame or a fire, because that environment has the potential to be a flammable environment. Okay? And so if we have gasoline or alcohol vapors or any volatile vapors in there, then what that means is if we have an open spark, we have the potential for a fire or a combustion hazard. So distillation is almost always in a classified environment. And so that's why it's, when we went to the lab, that's why it's in that concrete enclosure separated off from the rest of the processing facility. These are different types of trays. Depends on the internals of what we're dealing with. We have sieve trays, which are shown here. The sieves means they have just little holes in them that the vapors can go up and through, but they're small enough that the water doesn't want to quickly, easily, liquid doesn't want to quickly and easily fall down through it. Okay? The vapors can go up, but the liquids don't fall down through it very quickly. Okay, and then we have bubble cap trays shown down here. You can see some of these are down and some of these are up. What happens with these is they're not really permanently attached. They're just kind of held into place. And what these will do is as vapor pressure rises up, they'll lift up these bubble caps. Bubble caps will go up, allowing the vapor to escape. But keep in mind there's liquid on here, and so the liquid and gravity will make the bubble caps come back down. And then very similar to that, we have valve trays. Valves will open up as they get pressure underneath them. The vapor pressure underneath them will open up, allow the valve to open, and then once the pressure gets relieved, the valves close off, not allowing the liquid to go backwards through them. Okay, so those are three different types of trays that we have. In addition to trays, we also have packed columns, and we can have a combination of tray and packed columns as well. The whole purpose of either a tray or packing material is to slow that vapor down from going up too fast and to slow that liquid down from just falling straight down the column. Okay? We want the vapors to go up, but we need to be able to control it so it doesn't just go straight to the top of the column right away. And we want that liquid to fall down, but we want it to control it so it just doesn't drop to the very bottom of the column right away. Okay? And so if we have packing, this is kind of a way that we have that the vapors can go up and find their way through all this packing, but it's going to take it some time to actually go through and find its way all the way around and get up through the material, okay, as it gets packed in the column. This is what we looked at in the lab. We already looked at this already. Should look familiar to you. This is a distillation system that we saw already. And then that gets us into one of the last things, which is problems and troubleshooting and fixing distillation. And so here we have problems with distillation. Okay? And so you have your feed composition changes, which we kind of already talked about, as that feed material, as it goes from 20% to 30% to 25%, it's going to change how you have going out. And if you don't make that change, say you have a tray system coming in here, and you send it in, you start with 20% distillate coming in, and so you have it all set up and you have 20 gallons a minute coming out and everything's nice and balanced. That feed composition changes and you end up with 30% distillate, okay, because your reactor ran really good, really extra fast and really extra good. Then you're going to have to adjust this. So even if you're not adjusting the feed going in, you're still going to have to adjust your outlets coming out, okay? And that's as the feed composition changes. Okay, we'll talk about puking, flooding, and weeping next. So puking is just like kind of what it sounds like. Puking is when we have too much vapor pressure going up and it just shoots it way up the column really fast, okay? These trays or packing materials meant to slow the vapors from going up too fast. And if the column has any type of what we call puking, that means that vapor is so hot, such high pressure, moving so fast that it just shoots right up the column and the trays can't slow it down, okay? And that's puking. Okay, the opposite of that is flooding. When we have so much liquid going down really quickly, and it just goes straight down and overwhelms the column as well, okay? We want the liquid to go down the downcomers nice and slow, sit on the trays, okay, go through, go down. But if we end up overloading this too much with liquid, we end up flooding the column, that means that vapor can't rise up through the column because there's just so much liquid coming down, liquids going in between all the trays, liquids everywhere. We can't get that vapor to rise up, which means eventually that vapor is going to get carried down with the liquid and just cause more of a problem. Okay, so we want vapors rising up, but not too fast that they're puking, and we want liquid flowing down, but not so fast that it's flooding. And the third one here, there's weeping. Weeping means we don't have enough vapor pressure. Okay, vapors are moving up the column. Okay, vapors working on our trays, pushing up the column, keep that liquid from falling down through the trays. Okay, so when we have our different types of trays, we need to have that vapor pressure holding that liquid on the tray. Okay, whether it's a sieve tray or a valve tray or a bubble cap tray, or even packing material, we need to have a certain amount of vapor pressure just holding that liquid up, allowing that liquid to flow down gently and easily. Where if we don't have enough vapor pressure holding that up, then the liquid just goes down too quickly. Okay, and that's weeping. We don't have enough vapor pressure. And the last one here is overloading. That's where we're just running the column faster than what we can actually get out of it. And that's where we have this going in, and we're only able to do 100 gallons a minute, but operators want to go faster. They want to get more product through, and so they bump it up to 110, 120 gallons a minute. And again, just like I said before, you're not going to notice anything right away. You're not going to notice anything for an hour or 2 hours, but eventually you're going to be overloading it where you can't have full separation. And so that means we either have bottoms product go out our distillate line, or we have distillate go out our bottoms product line. So one of the two is going to end up happening, and that's overloading. Okay. These are all different things you have to troubleshoot. We'll look at these a little bit when we go into Centronics, and we'll end it here, and we'll look at Centronics, but we'll kind of talk about most all of these as we go through that. All right, good, right on time. Any questions before we jump into looking at a distillation column in Centronics? Okay, so as we have this distillation column here, this is our overview page. What we're doing with this distillation column is we're separating out hexane and heptane. Okay, very similar components, but they're different enough we have to separate them out when we're dealing with oil refining and gasoline. Both components go into gasoline, but we need to be able to separate them out in order to get the proper blends and proper octane of gasoline, get it to the proper levels. So what we have here is we have our feed supply going in, and that goes into our heater, okay, our feed preheater. Feed preheater, which is going in here through our feed pump. Okay, after it goes through there, what we're doing is we're getting it to the optimal temperature. Okay, that optimal temperature happens to be around 176 degrees or 180 degrees. Our hexane is going to boil around 156, 160 degrees. Okay, it's going to boil at 160 degrees. But then our heptane, which is our heavy material, doesn't boil until 210, 209 degrees, somewhere around that neighborhood of 209, 210 degrees. Okay, and so what we do is we bring it in the middle of that. Okay, in the middle of 150 to 200, we end up at 176. Okay, and that way the light material, a lot of light material is going to vapor, boil off, go to the vapor. Heavy material is going to be liquid, and they're going to fall down the column. Okay, as the material goes out, this light goes out to distillate, goes through this condenser, goes into our accumulating drum, and then our accumulating drum collects it as a liquid form because it's been condensed, and then it pumps it back through this reflux. Okay, now if you'll notice, reflux sends 200 gallons a minute, okay, back as reflux, and 120 gallons a minute go out as overhead product. Okay, generally that's anywhere from 1/3 to 2/3 of our product goes back as reflux, depending on how much we need for the how hard this is to separate. Okay. So we have the reflux go back in, that's our cooling to the column. And then as material goes down, we have our bottoms, we have our reboiler here. Okay, reboiler is going to boil the material off. Again, bring it right up to that boiling point. The boiling point of heptane is 209, 210 degrees, depending on the pressure. And so we bring this up to 204. Okay, so we're bringing it up right to its boiling point. So if it's staying a liquid at 204 degrees, we know that it's all heptane, it's all bottoms product, and it can go on out down the column. Okay. Now, if you notice, we have 235 gallons a minute coming in. We have 113 plus 121 and change coming out, which equal 235 gallons a minute coming out. Okay, so that's where we have to have our material balance. Whatever's going in has to eventually go out. Okay, and so we can adjust this, or we can mess with this and see how this responds, but and go from there. Now, as we look at this in more detail, this is what the feed system looks like. Okay, this is where we're at. We want to hit that temperature on our feed tray. Okay, feed tray happens to be halfway up the column. Everything above the column is a rectifying section. Everything below the feed tray is the stripping section. As you notice, as we go up the column, we end up getting lower and lower in temperature, down to our 156 number. Okay, that's a boiling point of hexane. As we go down the column all the way to the bottom, we go down all the way to the bottom. We end up at a higher temperature of 204 degrees, just below the boiling point of our heavy material. Okay, heavy material boils at 209 degrees Fahrenheit, so we bring this up to 204. 204 degrees Fahrenheit is plenty hot enough to know that if there's any hexane down here at the bottom of this column, it's going to boil off and it's going to go back up to the top of the column. Okay, we know the pressure of the system, it's at atmospheric. We know the temperature of the system by measuring it. We use those two things to be able to determine what the concentration of hexane is in our column. Okay, we happen to have 91% hexane all the way at the top. As we go down, our concentration of hexane gets lower and lower and lower until we're down to 7.3 all the way at the bottom, concentration of hexane. Okay? So the higher we go up, lower the temperature, the higher the concentration of distillate. This is just focused in on the bottom of the tower. Okay, we have our feed pump. We have our reboiler here that boils the material up again. Okay, we heat it up to 204 degrees. Anything that stays a liquid all the way at this point, we know, we're pretty confident this is heptane, so it goes out to our bottoms product storage tank. Okay, the thing that Centronics is missing here that we often have is going to be some kind of cooler. Typically, we cool this, and we won't store it at that 204 degrees. Okay, that'll be on down the line. And then if we look at our overhead view, this is where we're coming off in our vapor form. This is where we're condensing it. Okay, and it goes into our reflex accumulating drum, and it should all be in the liquid at this point. All the liquid gets pumped back through this pump. Some of it goes out. Roughly 1/3 of it, just over 1/3 of it goes out as overhead product. and just under 2/3 of it goes back as reflux. Okay, so it goes back through reflux. We have about 320 gallons a minute coming up through here, going through our condenser. 120 of that goes out the overhead product, and 200 of that goes back as a reflux, providing cooling to our tower. Okay. Now, what I want to show you, one of the quickest and easiest things to show you is what happens if we have a problem with our reflux. Okay. Once I start this Femtronics simulation back up again, what's going to happen is we're going to get some fouling in this heat exchanger. If you remember back from safety class or equipment class, fouling of a heat exchanger is where we start to get deposits on the tubes of our heat exchanger, and we can't exchange the heat, or we can't transfer the heat as efficiently. And so rather than us cooling it down nice and good and gets it down all condensed down in the liquid, this is going to stop condensing it as well. And so what's going to happen is we're going to see what it looks like after, as this goes. We're going to watch it, and we're going to be able to see when we have a problem with this condenser. When we have a problem with this condenser, that means we have a problem with the reflux, and that's going to throw our entire column off. Okay, this will show you what it looks like when we have a problem with just one piece. Okay, so again, we have 235 gallons a minute of material coming in. Roughly half and half split, okay, of material. So it's starting out, it's half and half heptane and hexane. And we get a lot of that separated out through our overhead product. And then everything else comes out on our bottoms product. We use heat to heat it up initially, and then we use heat to reboil it again, and we're cooling it in our condenser. I'm going to show you an example of what happens if we have a problem with our condenser. Okay, we have a problem with our condenser. So right now, if you notice, we're at 161 degrees here at the top. Notice we're at 156 degrees, what's coming in, condensed product, and watch those temperatures change. We're going to start to see these temperatures go up. We're going to see these temperatures go up because we got a problem with our condenser right here. We can't cool this material off. We can't condense it back down into its liquid core as efficiently as we were before. Okay, so we see these temperatures go up. First, we think, oh, that's no big deal, just a little bit hotter. But watch what that does to the rest of the column. Okay, watch what that does to the rest of the column over just a few minutes. Watch what happens to these temperatures. All these temperatures are going to start going up. Okay? The reason all these temperatures are going up is because we're not cooling that material at the top of the column enough. Okay? We're not cooling it down enough, okay? Which means we're going to have higher and higher temperatures as we go throughout the column. Also, look at what happens to our concentrations over here. We end up having higher concentrations of hexane going in over here, which is going to cause us to overlap. We're going to get too much of that material. We're not going to be able to separate it all out. Okay? If you remember back from equipment class and intro class, what happens when temperature increases? Also pressure increases. We were operating right at atmospheric pressure at 0 psig. We're all the way up to a half, now 0.6 psig. And so in addition to us getting hotter, now not only that, but our boiling points are changing. Okay. Meant to block that out before we started, but anyway, horn silence. So now we're getting alarms. That stuff is not operating the way we want. Okay, after just 2 minutes. And so now we're all the way up to almost 1 psi, which is going to drastically change the point at which this material is going to boil. Okay, so what's happening is our hexane no longer is boiling at our 156 degrees Fahrenheit. Okay, now it's going to be boiling at a higher and higher temperature, which means our concentration of hexane all throughout the column gets hotter. It gets higher and higher and higher to the point where we're sending it out with our bottoms products. Okay. And this is all due to the fact that we don't have good, adequate cooling at the top of the column. Okay, so we don't have good, adequate cooling at the top of the column. Now, the other thing that we haven't gone over yet is this accumulator drum, this reflux drum. Now, this is where after it gets condensed, turns into its liquid, okay, it gets turned into its liquid and gets pumped back in the tower. At the beginning of this, we had nothing going off this top vent line, and I just ignored it. But what we have now is we have this valve opening, this PV701, this pressure valve, because we're getting too high a pressure in the system. We want to be at 0 atmospheric pressure. Okay, now we're up to 2 psi. The reason the pressure is increasing is because we're not cooling this down. Our temperature is now increasing. We were at 156 here, now we're up to 165. Higher temperature means higher pressure. This reflux drum can't handle a high pressure, so it has to vent. Okay? It has to vent out to the flare. And so now we have material, instead of being separated out, it's going into product storage, it's being vented out to a flare and just getting burned off. Okay, so we're just losing product out the vent at this point because we aren't cooling it down enough. If we didn't have that vent, this would overpressurize and eventually we could have something catastrophic, rupture in that case. Okay, and so we see this happening, and we have this venting off. When we have this venting off, that causes an upset with all the rest of our controls. Okay, that causes an upset. We no longer have material 121 gallons a minute going out our overhead product because so much is going out through our vent. Okay, we have material going out through our vent instead. Okay, and so if we go back to our column profiles, we were low 160, now we're getting up and up and up and up, even higher and higher and higher, hotter than what we want to be. Okay, all throughout. We're up to 3 psi, so even though we're higher temperatures, still don't know where things are boiling at because we keep changing that boiling point. And so if we want to see what this looks like over time, we can pull up our temperatures. Okay, and our composition and our temperatures, and they're all just increasing. Okay, and so we're no longer separating out by boiling point as effectively as we were before. There's still some separation happening, but instead of getting all the material out the distillate and then all the other material out the residue, they're blending, and we're getting that overlap, all because we have one valve condenser. Okay, and so you can see we're no longer sending this yellow line. We're no longer sending product out the overhead. Okay, now it's all going out the bottoms. So if we look at this product going out the bottoms here in this yellow line, we're sending it all out the bottoms instead of out the overhead because of what's going on with our condenser. Okay, so one heat exchanger fouling, one heat exchanger not working up to its potential throws the entire system out of whack and throws the entire system off. Okay, so everybody see this? Does anybody have any questions about distillation, about what's going on with this Centronics? Okay, one heat exchanger can't cool enough, and so that causes all of our temperatures to increase, causes our pressure to increase, which causes everything to get thrown off of whack. We no longer have that balance, no longer have that material balance, we no longer have that heat balance. All right, so we separated by boiling point. That was distillation. We have another way that we can separate two or more materials, and we can do that through extraction. Okay? The reason we use extraction over distillation, primarily where you go work, industry, you're going to use distillation. Okay, it's going to be a little bit cheaper, easier way to run things at a high throughput. If we can't do distillation, then we can go to extraction. A couple of the reasons for extraction. If the boiling points of the material are too close together, so if we're trying to boil material that doesn't have, say, 40 or 50 degrees difference in that boiling point, then we can't separate it by boiling point. Okay, so if we have two or more materials that boil just too close together, then we're going to have to use extraction for that. Or case of heat sensitivity. So if we're trying to separate biocomponents, right? So we're trying to do some type of organic compounds where if we heat them up too much, that's just going to alter them. They're too sensitive to heat, then we would need to extract them. We'll show you an example of what that looks like today. And then the last one is the amount of material. Example of this is if we're trying to take ocean water, salt water, and turn it into drinking water, salt in it, we can't just drink it right away. We want to clean it up, but there's just not enough that we have to run all of that water through a distillation column. It would take way too much time and money and energy to boil all the water that we would need. And so we have to come up with a more economical method, okay? And so those are all reasons that we have for extraction, okay? What we have, we're gonna look at is the single stage extraction on the left of your screen here. That's where we're mixing a feed with a solvent. And what that solvent is going to do is it's going to dissolve half of the feed, and that's going to dissolve half the feed, go out as extract, and it's going to leave half of it as our good, clean product that we give it a term of raffinate. Okay? That's what we're doing. We're basically dissolving components. Okay? This is the way we do it in industry. We do it counter current. Okay? Concurrent extraction just doesn't make any sense. It doesn't work very well. It's not very common in industry. The counter current is what you see and is what the most common way is. Okay? And that's where we have our feed come in, as shown over here on the left. And then as that feed comes in, it goes through each one of these stages. As it goes through each one of these stages, it gets cleaned up more and more and more by this solvent. Okay? Solvent comes in on the top right, and it goes through the system. Solvent, as it goes through, it's going to dissolve the solute, or the part of the feed that we don't want anymore, and that goes out as extract, kind of like residue. The part that it doesn't dissolve is our good, clean product that we call raffinate. Okay, and so that's what we have. Now, what does this look like, and what throw out these new terms for you: solute, solvent, doesn't matter. Let's look at what an actual example of this is. Okay, and we go back to Phillips 66 down there in Wood River. This is exactly. This is a way that they do it. This is a way that we have to clean up crude oil. Okay, what we have with crude oil is a bunch of other stuff in it besides just oil. Okay, and it's kind of dirty or salty. Not always just salt, but there's other contaminants and components in it. And it would really damage our equipment if we ran it through our systems. Okay, if we ran it through our distillation columns or our reactors, and so we need to clean it up. Okay, and so we need to clean it up. What we can do is we take that crude oil with a bunch of salts and minerals and stuff in it, and we simply run it through with water. Okay, and in this case, water is our solvent. So if we start with our dirty, salty crude oil down in here, and it goes up into our extraction, what we do is we simply run water in here. Okay, we run water. We can get this water from any municipal source. It can be somewhat clean, even somewhat dirty if we want, because what that water is going to do, that solvent's going to do, is it's going to take, and that water is going to grab onto this salt. Okay, right? So if we have salt and we have water and we just pour the water into a bottle, pour salt in, it's going to want to, it's just going to want to mix up with the salt. Okay, it's going to want to dissolve the salt. And what's that water going to do to the crude oil? Nothing, right? Water and oil don't want to mix at all. So that water is going to stay away from that crude oil. It's going to grab onto that salt. As it grabs onto that salt, what do we make? We make salt water. Okay, that salt left the crude oil, went into the water, and so what we're left with is a good, clean product of clean crude. Okay, so desalted crude. And so as that salty crude oil goes up through here, crude oil is lighter than water. Okay, so crude oil, if we have oil and water mixed together, oil is going to float on top. Okay, so it's lighter than water, it's less dense than water, and so that crude oil is just going to go on out cleaned up without the salt and go out this line called raffinate. The water, our solvent, is going to dissolve our crude. It's going to dissolve the salt that's in our crude, and that's going to go out the bottom. It's going to be called extract. Okay, that's what we do. That's how we work it out. That's how we clean up the crude before it actually goes in and does any distillation or any type of reaction processing. Okay, as we get the salt and the minerals out of it first. Another example of this that we can do is, and the reason why we do it this way, not oil refinery, is because there's salt in it, and that salt's damaging. We can't have it run into our system, but there's not enough salt to justify boiling all this crude off. Okay, just not. It's just way more economical to just run water through it than it is to try to increase the temperature of this crude oil all the way to the point where it's going to be boiling off and leaving the salt behind. It just, distillation just doesn't make any sense. It doesn't make as much economical sense at this point. We wouldn't be able to do that. This other example is where if we have problems with heat, okay? Here, if we had tried to distill this by adding heat to it, it would damage our product, okay? And so here, what we have is we have this feed that comes in. This feed happens to be butanol and water. And we have this special oil that we have as our solvent, okay? Call it vegetable oil, but it's not really vegetable oil. It's a special, something, it just looks like vegetable oil, but it's a special oil that'll actually mix in with the water. And what that special oil does is it mixes in with the water and leaves pure, clean butanol left, okay? This is another example of where we use extraction. But the reason we could do this, we could separate out butanol and water. We could separate that out by boiling point, but if we do that, then that's going to damage our butanol that we have, that butanol mixture that we have. And so we don't want to damage that by increasing the temperature of it to the point where it's vaporizing. And so what we do is we can just use a solvent extraction. Okay. Now, what are we doing this in? This process, well, it's going to look very similar to distillation. It's going to be in a tower. We can have packed, we can have trays just like before, or there's a third option of mechanical. I'm not going to spend any time on packed and tray because it's just like distillation, packing material or trays. The third option is we have a mechanical. Mechanical column means there's going to be an agitator in. In order for this to work, in order for this solvent extract to work, it's got to come into contact with the feed. If we just have a big giant 500,000 gallon tank and we just have one stream over here and one stream over here, and they never actually come into contact with each other, it's not going to be able to extract. And so, very common way that we have is we have agitators in them. Okay? Those agitators, we call that a mechanical extraction. And those agitators make sure that solvent, that feed, come into contact with each other so that they can do their thing and dissolve it. Okay. That's the end of extraction. So other separation systems, we've already kind of talked about this. This is a scrubber. We use this in the utilities chapter. So we talked about our scrubber. Here we have gases coming out with CO2. Okay, what we can do is we can clean that CO2 up, okay, or we can clean those waste gases up, and we can clean those waste gases up and we can collect that CO2 with a scrubber if we wanted to. This is something that we talked about in the utility chapter. This is something that over where we do our labs at the ethanol plant, they don't do, but a lot of ethanol plants do because they're bigger, okay? Where we have CO2, they just emit it out to atmosphere because there's not enough to really do anything with. But other ethanol plants will actually bottle that up and sell that as a inerting gas or sell it to Coke and Pepsi where they can carbonate, or Anheuser-Busch or places like that, they can carbonate beverages with it, put CO2 into carbonated beverages. And so in order to do that, in order to use that, it has to be cleaned up, okay? And so in order to clean it up, one way that you have is a scrubber, okay? That scrubber happens to have an absorption gas or an absorption liquid that's going to go down across that gas. As the gases float up, that liquid's going to go down and it's going to absorb in that CO2. And then that absorbs its CO2. We clean that up, okay? It's going to allow the waste gases and the other waste gases to go out through our flare system. And then the carbon dioxide gets trapped and gets added in here. Okay, and this shows us something else that we haven't talked about yet is we have that solvent. Once it picks up whatever we're trying to dissolve, it needs to be cleaned back up so we can reuse it. If you remember back to our first example, at some point what we're left with here is salt water. Right now we can't just dump that salt water back into the sewer system. We can't just dump it back into the river because that wouldn't be good environmentally, right? So we have to, last step of this extraction is we have to clean that up, okay? And so typically what we do is we clean that up by filtering it out. Okay, so we filter out that salt, filter that out of the salt water. to clean that out. But there's always going to have to be some way that we get that solvent cleaned back up so that we can reuse it again in the process. Okay. Another method that we have besides absorption and extraction is adsorption. Adsorption, notice the D, adsorption. Just think of that as like adhering. So what does tape do? If you stick tape on your arm, tape adheres to your arm, or tape adheres to something. It's an adhesive, it sticks to it. Okay, adsorption means something sticks to it or clings to it. Okay, in our water treatment that we looked at in the utilities class, that's what we have, that sticking to that membrane, sticking to that filter. Molecular sieves, we'll look at this when we get back in the lab a little bit more, but that's where we're going to have a little bit of water come out the top of our distillation column. We want to be able to collect that, and so we'll run that through molecular sieves. And we'll talk about that more when we get in the lab, but those are little porous beads that will actually have water stick to it, okay? Ethanol won't stick to it, but water will, okay? Another thing is silica gel. So if you've ever bought any clothes and got that little silica gel packets, those will absorb water, okay? So water will adhere to that silica gel. And then the last one is activated charcoal. So this is what we have in respirators, okay? So the respirators, if you ever used a half face or full face respirator, we learned about them in safety class. That's what they use, is they use activated charcoal. Activated charcoal will have any of those hazardous and contaminant gases adhere to the charcoal, allowing the oxygen to pass right on through. Okay, that's all ways that we have of adsorption. And we'll talk about this when we get into the lab later with the molecular sieves. Okay, so we'll go over regeneration once we get into that in the lab again, which will be next week. These are two more things that I don't want to spend too much time on today. I want to talk about them when we get them into the lab. We'll throw some videos up from YouTube, and we'll talk about them in the lab. And that's where we're separating solids from liquids. So the last thing that we're seeing here is not in your textbook from chapter 16. This starts to move on to what we're talking about next week and the following weeks, and that's where we get into solids handling material. Okay? That's what's happening with the centrifuge and the filter press, is we have a liquid and a solid mixed together. Okay, that's our feed system. We call that a slurry a lot of times, and that feed, or a sludge or slurry. And what that's going to do is we're going to need to separate the liquids from the solids. And so how do we do that? Well, that's the way we do that is a lot of different ways. The two of the most common in industry is a filter press and a centrifuge. We got them both in the lab, so we're going to look at them both in the lab whenever we get in there. And then from there, we're going to talk about how we can handle some more of the solids and stuff that we haven't really talked about. Talk a lot about liquid moving liquids, flow meters, different things like that. That's going to bring us into talking about how we handle solids, okay? So those two things that we haven't talked about yet. And then the other thing is drying. We haven't talked about from chapter 16 yet as well. We will cover that in the lab as well as drying. So drying and then solids handling is what we're coming up to next. Okay, so once you get to adsorption in the book, which stops on page 462, you're kind of done with chapter 16 for now. Okay, so chapter 15 we covered all of it, and then chapter 16 we just kind of go over half of it, and then we'll meet in the lab next week and kind of finish that up. Any questions about chapter 16 so far?